Welcome back to the Deep Dive. Today we're looking at something pretty transformative, a new model called DreamOmni 3.
And it really is a huge shift. We're finally moving on from just typing text prompts.
Right. It's about giving you direct visual control, freehand control, just by using, simple scribbles.
Which fixes what I think is the biggest single pain point with AI art tools. I mean, language on its own is just, it's too imprecise.
Totally. You can't just tell it, change that specific branch on the third tree from the left.
Exactly. It's
Yeah.
impossible to define those really fine-grained details or to tell apart two identical objects. To get that kind of precision, you just have to draw it yourself.
So what does that drawing actually let you do? It seems like they've opened up a couple of new areas here.
Two big ones, yeah. First, you can use scribbles for editing an image that already exists, things like doodle editing or even image fusion.
Okay. And the second?
The second is using scribbles for generation. So starting a brand new image, basically, from your sketch. And that works for concrete things like a house, but also for abstract stuff.
Like changing a hairstyle or a color scheme with just a quick scribble.
Precisely.
That sounds amazing, but I have to ask, if I'm drawing right on top of the image, doesn't that create a new problem? Like, the AI can't see what was underneath my scribble.
That is the exact technical hurdle they had to solve, and it's why this is such a breakthrough. The old way would be using something called binary masks.
Black and white maps, basically telling the AI where to edit.
Right. But they're clunky, they're computationally expensive, and they don't work well with multiple edits or with language instructions.
So what's the big aha moment here? What do they change?
It's their new joint input scheme. And it's actually brilliantly simple.
Okay, so break that down. Joint input.
Instead of feeding the model one thing, they feed it two things at the same time.
Two things.
Yep. The model gets the original untouched source image, and it also gets the source image with your scribbles on it.
Okay. So it sees the before and the after at the same time. Why is that so critical?
Because, like you said, the scribble covers things up. It obscures the pixels underneath. If the model only saw that version, it would lose the original context.
It wouldn't know what it's supposed to keep the same.
You got it. So one input tells the model what to keep pristine, and the other tells it what to change. And they make them share the exact same internal encoding. So they line up pixel for pixel. Perfect alignment.
And the results really back that up, don't they? I saw that in human evaluations it came out on top.
By a long shot. And you can really see why when you look at the competitors. They just don't have this kind of context-preserving framework.
What kinds of problems were they seeing?
Well, with a model like GPT-4o, there were a lot of artifacts. A weird, persistent yellowing issue, for instance. Or you'd see a clear mismatch in pixels in the non-edited parts.
It just doesn't look seamless.
Not at all. And another one, Nano Banana, it had this weird copy and paste look. Proportions were all wrong. Dreamy 3, on the other hand, keeps the rest of the image absolutely untouched. Consistent.
I have to imagine that to get this right, the amount of data they needed was, well, it probably didn't even exist before.
It didn't. They had to create it all. I mean,
Yeah.
No one had built a large data set for multimodal instruction that also included freehand visual control.
So they were creating the instruction sets from the ground up.
Yeah, and at a huge scale. We're talking about roughly 32,000 samples just for the editing part, and another 16,000 for image fusion. It was a massive effort.
So wrapping this up, what it really means is that DreamOmni 3 has managed to unify language, images, and now our own sketches into one single system.
Right. It's moved beyond just being a descriptive tool. It's now genuinely interactive.
It feels like it finally bridges that gap between, a super technical professional image editor and the simple, intuitive act of just drawing an idea.
It makes this incredibly complex AI feel accessible. You just sketch.
So here's something to think about. AI creation tools began as just a text box you typed in. Now they're becoming these responsive digital canvases where a rough sketch can guide a final, high-fidelity result. It makes you wonder if the AI is becoming less of a prompt interpreter and more of a genuine artistic co-creator, one that responds directly to your touch.
Welcome back to the Deep Dive. Today, we're looking at this growing pressure on the huge AI models. You know the ones. Hundreds of billions of parameters, massive compute, huge costs.
Right.
But the future isn't just about those giants. It's got to be about efficiency. We're unpacking how researchers are making lightweight models that can actually, think strategically.
And that's our whole mission for this deep dive. We're getting into the technical report for Youtu-LLM from Tencent Youtu Lab.
It's tiny, right?
Exceptionally small, just 1.96 billion parameters. but it's built from the ground up to be a powerful agent. The real story here is they didn't just, distill a bigger model. They systematically taught this small model how to plan and reason.
Okay, so let's start with the engine under the hood. They stick to that 1.96 billion parameters and use a dense multi-latent attention, or MLA, architecture. So why do that? If mixture of experts, or MOE, is kind of the gold standard for scaling the big models, what was the trade-off they were making here with MLA at this, well, tiny scale?
It's a classic trade-off, really. For this kind of lightweight model, latency matters way more than total throughput.
Ah, on-device stuff.
Exactly. MLA just gives you better expressiveness with fewer parameters, and it's much better for a low latency on-device deployment. MOE has all that communication overhead. But you hit on the core problem. Models this size usually just. They completely lack the planning, the tool use, the reflection skills you need for real agentic behavior.
So the architecture is one thing, but the real magic seems to be the instruction set they came up with. This structured thinking paradigm they call agentic hati.
Yes. It's disciplined pedagogy, really. Regular or vanilla chain of thought can just ramble on.
It can be all over the place.
Right. But agentic COT forces the reasoning into this very strict sequential workflow. They often use these like XML-style tags to structure the model's internal monologue into 5 specific phases: analysis, then plan, action, reflection, and finally a summary.
Okay, but doesn't that structure risk stifling creativity? I mean, if you force it into these boxes, can it still handle novel problems that don't fit the mold?
That's what's so fascinating. The paper shows the structure actually enables a better strategic choice. In a really complex math problem they show, this structure actually forced the model to choose a counterexample strategy to solve a ring theory question.
Instead of just brute forcing it.
Exactly. It shows real strategic planning, not just, calculation.
So if the structure is the key, they needed the data to match it, and the number is just staggering. They synthesized 25 billion tokens of this hyper-specialized agentic code data.
25 billion.
Yeah. Across math, code, deep research. That number alone tells you they treated this like a massive teaching challenge, not just a scaling one.
And the data generation itself was so specialized. For math, they used something they call an atomic thinking approach.
What's that?
Well, they broke down complex mathematical reasoning into 11 independent, verifiable cognitive abilities. So things like symbol recognition, deduction, and crucially, self-reflection. They were basically teaching the model to check its own logical steps.
And what about for more open-ended things, like deep research, where it's easy to just not dig deep enough?
For that, they use a think twice framework. Before it generates a final report, the model is forced to first summarize all the information it's gathered, and then it has to explicitly evaluate if that summary is sufficient.
So if it's not good enough, it has to go back.
It has to go back and explore more. It prevents it from writing a report based on like a shallow investigation.
That data synthesis must have been incredibly noisy, though, with all the tool calls and queries. How did they filter out the irrelevant parts during training?
They did, and it was a clever trick. They used masked loss calculation. For tool use and research scenarios, they basically told the model to ignore the tool's response, the system prompts, and the user query when calculating loss.
So the model is only graded on its own thoughts.
Precisely. It forces the loss to focus exclusively on learning its own internal reasoning and action generation.
Yeah.
It cut down the noise and made the training way more efficient.
So when we look at the results of all this specialized training, this common sense STEM agent design, what was the payoff? What did that agentic mid-training phase actually get them?
The payoff was huge. Adding those structured agentic code trajectories gave them a consistent and really significant performance uplift. I'm talking a relative improvement of 14.4% on agent benchmarks.
Oh.
The takeaway is pretty clear. Getting high performance out of small models isn't about distillation. It's about systematically building these intrinsic cognitive skills through disciplined, structured data.
So the ultimate lesson for you is that thinking like a giant isn't about having a giant's brain. It's about being taught how to think structurally. These efficiency gains are enormous, but, the focus right now is all text-based. So given how effective they were at optimizing the process of thought, what challenges, especially around something like inference latency, do we have to overcome before these lightweight, smart agents can be efficiently deployed into real-world multimodal scenarios? Something for you to mull over until the next deep dive.
Welcome back to the Deep Dive. Today we are tackling what is arguably the biggest bottleneck right now in generalist robotics.
Yeah, it's a big one. We've got these incredible vision language action models, VLAs, that are fantastic at following instructions.
But they've been stuck. They're almost all attached to these, simple pincers, just 2 or 3 finger grippers.
Exactly. And if the real goal is human-level manipulation, that's just not going to cut it. You need dexterous hands. High degrees of freedom hands.
We're talking about a huge leap in complexity here.
Oh, it's exponential. You go from a few joints to dozens. The control space explodes, you get constant occlusion problems, and the cost of collecting data is just, oh, it's astronomical.
Which brings us to today's source. We have a technical report from ByteDance that claims to have a solution, GR-Dexter.
That's right. They're proposing a whole framework, hardware, model, and data all working together.
So our mission for this deep dive is to unpack exactly how GR-Dexter scales these VLA policies to get this, a 56 DUF bimanual robot system.
56, it's an incredible number.
Okay, let's start at the foundation, the hardware. What are they building on?
So the core of it is their new hand, the ByteDexter V2. It's really engineered for this. It's compact, it's anthropomorphic, so it looks a lot like a human hand.
And it's not just about looks.
Not at all. It uses this really ingenious linkage-driven system. And crucially, each hand packs 21 degrees of freedom.
21 per hand. Wow.
Yeah. The thumb alone has 5, and then each of the 4 fingers has 4.
So that's how they get to such a high number. They're not just tacking them onto any old robot arm.
No, they're deploying 2 of these V2 hands on a dual-arm platform, specifically 2 Franca Research 3 arms. You add up the arm and the hand duffs, and that's how you hit that headline number, 56 duff.
Built for two-handed tasks from the ground up.
Precisely. And what's really fascinating is they've integrated these high-density piezoresistive tactile sensors right into the fingertips.
So it has a sense of touch.
It has a sense of touch, yeah.
Yeah.
Crucial for delicate work. They report it can pull off all 33 of the FAX grasp types, which is basically the entire dictionary of human grasping.
Okay, a 56 DUF system is just staggering. I mean, that's more joints than a human has in both their arms and hands. How on earth do you train something like that without needing infinite data?
That is the million-dollar question. And this is where their real innovation comes in, I think. It's what they call their data pyramid.
A data pyramid. Okay, break that down for me.
It's a multi-layered strategy. So at the very top, the most valuable, most specific data, you have teleoperated robot trajectories.
So a human is driving the robot.
Right, but they made it super efficient. They use a custom VR setup, a MetaQuest headset, and Manus gloves, which lets them retarget human motion in real time. This is how they got demonstrations of incredibly complex tasks. We're talking knitting, writing calligraphy.
Wow. Okay, so that's the super high quality layer. What's underneath that?
Well, to get generalization, they need more. The next layer is just massive web-scale vision language data. This is just to train the VLM backbone so it understands language.
Makes sense.
Then they pull in cross-embodiment data. So they're using existing data sets from other robots, like the Open Loon Baihu. They're not reinventing the wheel.
And the base of the pyramid.
The base is over 800 hours of egocentric human trajectories, human videos. Now, they have to filter this data really carefully and retarget it because of the kinematic gap, the physical differences between a human hand and the robot hand.
So let's talk payoff. What can this whole system actually do?
This is where it gets really impressive. It excels at these long horizon everyday tasks. The report gives examples like bread solving with tongs. One hand uses the tongs, the other holds the plate.
Real coordination.
Exactly. Or vacuum handle, grasp and sweep, where it has to coordinate a 4-finger grasp while the thumb is busy pressing the power button.
That's quite specific. But what about generalization? When you throw it a curveball?
That's the biggest breakthrough. They tested a makeup decluttering task. Now, when faced with a table layout it had never seen before, what they call out of distribution, a plain VLA baseline model, its success rate dropped to 0.64.
Which is not great.
Not great. But GR-Dexter, with its data pyramid, its success rate jumped to 0.89.
That's a huge leap. That shows it's actually learning the underlying task, not just memorizing layouts.
It's robust generalization. And because of that deep VL data, it can follow really abstract commands, things like pick up the darkest object or even pick up the drinkable object.
So tying this all together, what's the big picture here?
I mean, GR-Dexter really proves that VLA policies can be scaled to these super high-def dexterous systems. The key insight is you can't just have one piece. You need the novel hardware, the simplified teleoperation, and this really clever multi multi-layered data mix to beat that complexity barrier.
A really profound step forward. But, the authors themselves noted a limitation. The hand and arm are still controlled as separate parts, which can hinder that super tight coordination.
Yeah, there's still a bit of a disconnect there.
So here's the thought for you to chew on. What if the next step is a single, unified model that controls the entire 56 DOF system as one integrated unit? What would that kind of seamless control unlock for, say, general assistants in our homes? Something to think about until our next deep dive.